Let's talk about the function sine x over x. It's a pretty cool looking function, very wiggly, and it makes a nice tall peak right at the y-axis. At the top of that peak there's a missing point, and that's due to the fact that x equals 0 is not part of this function's domain. It would be undefined at x equals 0. So that point is missing. We have a hole in the graph. We can still talk about the limit as we approach x equals 0 for this function, and we can start by looking at it graphically. Picking a point left of 0 and watching where it goes, picking a point right of 0, watching where it goes. We can see that the two-sided limit does exist. These 2 points went to the same location, but we don't know what that location is. We can't simply plug 0 into this function because we get a 0 over 0 indeterminate form, and none of the techniques that we have up till now can handle this. I cannot simplify by factoring. I cannot use a conjugate. I cannot use a common denominator to reduce a complicated fraction. None of our techniques work. We need a new mathematical method. The squeeze theorem is that method. To demonstrate the squeeze theorem, we're going to start by looking at another function. It's similar to sine x over x, but it's x times cosine x. It has a linear factor, x, and it has a trig factor, cosine x. So it's similar enough that we can demo our technique and see that it'll be helpful for the other function. But what's nice about this function is that it is defined at x equals 0. I don't have a hole in my graph. And since I know the function value at x equals 0 and I can see the graph, I know that the limit will be equal to the function's value at that point. So we know that the limit exists and that it's equal to 0 for this function. Let's demonstrate how the squeeze theorem can help us arrive at that exact same conclusion. X cosine x is on the screen. The squeeze theorem requires us to find a function that's always above our function and a function that's always below our function. So we'll pick something like the absolute value of x to be the function always above, which means x cosine x is always less than or equal to the absolute value of x. And we can pick negative absolute value of x to illustrate a function that's always below. So we can say something like negative absolute value of x is always less than or equal to x cosine x. And we create this string of inequalities showing that our function, x cosine x, is being squeezed between two other functions. And if we're interested in investigating the limit where x goes to 0, we can look at it graphically by picking some points on the function and watching them travel along their curves heading towards x equals 0. Notice that the points on the absolute value graphs travel straight towards 0. The point on the x cosine x wiggles, but it also goes towards 0. And the two absolute value points are getting closer and closer and closer together, squeezing the point on the x cosine x curve. Let's see that again for the points right of 0. We can see that all of these points are heading to the same place. So we can say that the limit, while x is heading towards 0, for the absolute value of x, for negative absolute value of x, and for x cosine x, they're all heading to the same spot, which means their limits have to be equal to each other. They're being squeezed together. Let's walk through the process. To use the squeeze theorem, we first picked a smaller than function and a larger than function. We apply the limit to each term. We evaluate the limit for the smaller function. Then we evaluate the limit for the larger function. It is very important that the limit for these two outer functions goes to the same place. That way, our next step is to say that the limit we're actually trying to evaluate is being squeezed between two numbers, and those two numbers are equal to each other. The only way for this inequality to be true is for that center limit to be equal to the two limits on the outer edges. So it must be true that the limit of x cosine x when x approaches 0 is also equal to 0. Now we can generalize this for any function f of x. If we want to use the squeeze theorem to evaluate a limit for some function f of x, we need to find g and h so that we can build this inequality. We need the smaller than function and the larger than function. And we have to make sure that the outer functions, g and h, have limits that go to the same value when we allow x to approach a. If that's true, then we can rewrite our inequality so that we have numbers on the outer edges of the inequality squeezing the limit in the center between them, which means we can conclude that the inner limit has to be equal to those limits that the other two functions were equal to.